So by now we understand that every pattern of charges create their own unique electrical field. So we started off looking at electrical potential because of a point charge. Now we are moving on to dipole. Two charges, one positive, another negative. So we are considering a dipole with minus q and plus q. Say let this be plus q and this be minus q. Separated by a distance of 2a. Say this is a and that's a and this is your center O. Let P be a point. Okay, we'll call this as P at a distance of R from the center O. Sorry, this is O, my bad. This is point P. I've already written it over here. At a distance of R from O. Let theta lie between the dipole moment vector and a line extended from the dipole midpoint to the point of measurement. So basically OP and your dipole moment. So the angle between them is theta. The direction of dipole moment is from positive to negative, right? Nope, other way around. Okay, guys, that's your direction of dipole. Too much of information already. Let me erase that. So this is your scenario. Okay, that's a unit away, and so on and so forth. Now, first thing first, how is that we'll be able to find the potential at a point because of two charges? Well, this is one point. I don't know if I mentioned or not. Voltage or potential, electrical potential at point P will be sum of potential because of positive charge and the potential that is generated by your negative charge. This is true by, yes, superposition theorem. Right, which states that the potential at P is sum of algebraic sum actually in this case. So I can just write it as sum. Please understand the difference between algebraic sum and vector sum of potential by positive charge and the negative charge, or any charge actually, by all charges. Okay, let's move on. Now let's substitute the voltage by a point charge, which is given by Q by R square. Is this correct? Wrong. It is Q square by R. Nope, this is also wrong. This is Q by R. So this is potential by a point charge at a distance R. Now, P will be equal to K Q by, say we'll call this as R1 and this is R2. So this is your positive charge and this is because of your negative charge, right? So where, so we have our, okay, R1 and R2 to be, I not named it, from positive Q to P and negative Q to P, right guys? Now, this is all that we can do with whatever we know. Now we have to go back to geometry. We have to express our final answer in terms of your dipole moment, then the distance from where, from the center to this, that is in terms of R, and your constant K and so on and so forth, and theta of course. So to do that, we need to make use of geometry. What geometry? Well, what I can do here is I can draw up a perpendicular line. Similarly, at the other end, I can draw another perpendicular line. So in this structure, I'll get this length to be what? Think about it. This will be, let me give you guys a hint. Wait, just a second. This is A and this is A. This length will be what? This length will be A cos theta. Similarly, this length also will be A cos theta. So where R1, the hypotenuse, is going to be approximately equal to R minus A cos theta. Agree? And R2 will be approximately equal to what? R minus A cos theta. Correct? Nope, it is plus. Look at it, look at it. Take a second. What are we doing? We are trying to get an expression of for, not of, for R1 and R2 in terms of R, which is this length, and the angle cos of theta, this angle. Right, guys? So how are we doing that? We are considering a triangle over here. So in this, we know the angle and we know the hypotenuse and we are finding the adjacent side. We did that. That is also okay. Looks good. Next, this length, right, is approximately equal to this length. Why? Because A is very small. Remember, an ideal dipole, the distance between the charges are almost zero. An ideal dipole, that is. So we can approximate this length, the entire length of R1 to R minus of this length. Does it make sense? And the entire length for charge minus Q, the perpendicular length, will be R plus of A cos theta. I hope that made sense. Now, moving on. What can I do with this? Well, substitute. As simple as that. So P is equal to K. Q is common. Brackets open. 1 by R minus A cos theta minus 1 by R plus A cos theta. Of bit of math over here. So taking LCM and all of that. So this is KQ R plus A cos theta minus R plus A cos theta. This entire expression divided by R square minus A square cos square theta. This math you guys need not show actually. R and R can get cancelled. And this step and all you guys need not show. You can directly write it as 2KQ. Of course, you should be able to do this in your head. A entire expression divided by R square minus A square cos square theta. So that is your actual expression. What if I have a case wherein R is very far away from the dipole? So what happens? The potential at that point will be equal to what? Think about it. R square minus A square cos square theta will be equal to what? Yes, it will be equal to approximately equal to R square. And therefore your potential will be equal to 2KQA cos theta by R square. But what is 2AQ? What is 2AQ? Think about it. 2AQ. Let me help you guys with that. 2AQ is where? 2AQ is dipole, yeah. Dipole, okay, it's here. Niche. I don't know if you guys are able to see now. Yeah, can you see that? What is that? 2AQ is nothing but your, yes, dipole. This has to be highlighted actually. It is a vector product. It's highlighted only. Just a second. This is entirely highlighted. Okay. Kind of. Now, let's go back to this. So I can rewrite this as 2p, sorry, 2 is used, kp cos theta by r square, where we have, on substituting, because dipole moment is equal to 2aq dipole moment, so that you guys remember. Now, you guys actually have this in your syllabus, specific cases. Find the potential of a dipole along the axis. You can learn this derivation and substitute what? We're going to substitute theta is equal to 0 degree and 180 degree. There are two possibilities. Let me explain it this way. See, this is your dipole, right? I can place it along this line, either to the left or the right. Is it not? So let me show it over here. That'll be a bit convenient. So say this is your dipole, right? The line connecting the dipoles, that is positive and negative. And we have this to be your, say, dipole moment. So this will be plus q, correct? And this is minus q, right? Wrong. This is plus and this is minus. Sorry, this is minus. Now, the angle along the axis means what? Along the line connecting them. So basically something like this, along this line. So if it's to the right, it is 0 degree. If it's to the left, it is 180 degree, because it is anti-parallel. Again, all this you guys need not write in your exam. This is for our information. Now, moving forward. So when we substitute theta as 0 degree and 180 degree, so we get P to be equal to, not P, sorry, capital P. Oh, not P, V. Why did I write P? I didn't even realize that. So V is equal to 2P by R square. And this is for theta is equal to 0 degree. So we'll call it as 0, 180 degree. This will be equal to minus KQ by R square. For theta is equal to 180 degree. So this is your minimum and that's your maximum. Other way around, yes. Again, you guys have to be aware. Sometimes I make mistakes wantedly and sometimes I make mistakes just like that, not knowingly. Human, right? So this is a case wherein we have the, oh sorry, again I wrote the same thing. Did I change it? This is a case of maximum, this is a case of minimum. My bad. Where a negative is there, so obviously this is smaller than that. So this is a case of maximum. So the potential is maximum along the axial line and minimum along the axial line, depending on where it is. Is it on the right or the left? With respect to the dipole moment, that is. Then the other case is your equatorial line. So this is minus q, this is plus q. So this is your equatorial line. So the angle between them is, yes, 90 degree. So cos of 90 degree is what? It is 0. Therefore, the potential over there is 0 volt. So along this line, the potential is 0. Reason being, potential is 0 because the charge in the elliptical dipole are equal in magnitude but opposite in nature, resulting in net effect being 0. So that's weird, is it not? Here we have the maximum, if you think about it, this side, along this length, and here you have the minimum. Maximum is of positive in nature, right? This is negative in nature. So somewhere along the line, we need to get a 0, is it not? So that's where your equatorial line is. Does it make sense? Of course, it can be either ways. Cos of 270 degree, even that is 0. So both the ends, it is 0, 0. You go this way or that way, so on and so forth. There are a lot of things that will match as and when you go forward. So you learn one chapter properly. This is the first chapter in this case. Everything else will fall in place. So please see to that, you will learn the first chapter properly. And of course, vectors and everything, all of those 11th grade syllabus has to be learned. Now, what is that we looked at? We understand that there are charges produce field. Field can be understood with the help of energy, that is potential, electrical potential. Electrical potential of different configuration will have different patterns. And that's what we're trying to learn. We started off with single charge. Now we're looking at two charges. That is nothing but your dipole. Dipole are positive and negative charges separated by a small distance. So potential at a point can be found by adding them up algebraically. It's not a vector addition, it's algebraic addition. So this is superposition theorem. As per superposition theorem, we can do this. Now, any point charge at a particular distance will produce this potential. And substituting that for plus q and minus q, we get this particular expression. But of course, R1 and R2 are not the same for both the cases, because we can have a charge over here. It is near to R1, but further away from R2. What I mean is it's near to plus q and further away from minus q. Agree? But we want to express in terms of R and theta and A, the distance between your dipole moments 2A. To express in that, we make use of a bit of trigonometry and we get this expression, and then a simple math and we have the answer. So along your axial point, we have two possibilities, a maximum and minimum. So if you guys happen to get in your exam, derive your axial point, derive the scenario wherein you are finding the potential along the axial point of a dipole, you can do this. Right, one derivation, you can use it in 3 places actually. You can also derive the potential of a dipole along its equatorial line. We can make use of the same derivation. Okay guys, now it's time for you guys to pause and have a look.